Okay, so in this video, we're going to be talking about symmetry, and we're going to start with symmetry of functions and relations, and then we're going to see how this gets simplified when we're only dealing with functions. Now, when we're dealing with general relations, we actually have three kinds of symmetry. We have x-axis symmetry, we have y-axis symmetry, and origin symmetry. And these things can happen either in combination or individually. Now, if we have an example of, let's say, y-axis symmetry, then what we're saying basically is that the graph looks the same side on either side of the y-axis. And so an example of that would be something like this, where we have this parabola, and you can see that on either side of the y-axis, the coordinates are happening at exactly the same time at the same place. They have the same value of same y value on either side of the y-axis. Now, x-axis symmetry is going to look a little different. So let's take a look at that. So x-axis symmetry is going to look something like this. And again, the idea here is that on either side of the x-axis, in this direction, points on this side are going to have the same x value as the points on the opposite side of the x-axis. So this is x-axis symmetry. And we also have origin symmetry, so let's look at that. Now, origin symmetry can happen one of two ways. So you can have it so that you have a situation like this where both your x coordinate and your y coordinate change sign as you switch over from the first quadrant to the third quadrant. So for instance, I have the point 1, 1 here, and then over here I have the point -1, -1. So that would be an example of origin symmetry. Another example of origin symmetry would actually to have both x and y symmetry at the same time. So another example like that would be something like this, where we have a circle. And again, if you look at the x-axis symmetry, it is the same both top and bottom. It's also the same both left and right. That has both x-axis and y-axis symmetry. But crucially, that also implies that it has origin symmetry as well, because if I look at a point over here in the first quadrant, it is mirrored by a point over here in the third quadrant, and vice versa for the fourth and the second quadrants. So both of these are examples of origin symmetry. Now, again, in the first case, this is origin only, whereas this is all three symmetries essentially simultaneously. Now, how would we go about establishing algebraically, not just looking at the graph, but algebraically, how these things are symmetric? Now, what we will essentially do is to test for y-axis symmetry. Since we want the y coordinates to be the same on both sides, so the same y value, different x values, we're going to replace the x in the equation with -x. And if we get the same equation after simplifying that we started with, then the equation is y-axis symmetric. Now, we have similar transformations we can do, similar checks we can do for the others. So to test for x-axis symmetry, we would do exactly the same thing, except we're going to replace y in the equation with minus y. And then if we get the same equation back that we started with, all of the minus signs cancel out, then it's x-axis symmetric. And to test for origin symmetry, replace both x with minus x and y with minus y. And again, if we get the same equation back after simplifying, then we end up with origin symmetry. Now, so again, this can happen either by the x and the y canceling the minus signs independently, or they can happen by the minus signs not canceling separately, but canceling together. So let's look at the graphs, the equations for the 4 graphs that we've looked at and see how each one of these works. So my first graph for the y-axis symmetry was just the simple equation y equals x squared. Now, if I replace x with minus x, again, keep in mind this is minus x times minus x. The minus signs are going to cancel. And I'm going to be left with 1 times x squared, which is just x squared. So the minuses cancel in pairs. I get a positive x squared. So this, again, confirms what we saw graphically, that this is y-axis symmetric. The second example, the x-axis symmetry question, was x equals y squared. And again, in this example, we're replacing for x-axis symmetry the opposite variable, which means we're replacing y with minus y. Now, for both of these examples, it's extremely important to keep in mind that the minus sign goes inside the square. So if it was 3 squared, it would become minus 3 quantity squared. So that's the thing that we're comparing. So the minus sign has to go inside the square. It's not minus on the outside x squared or minus on the outside y squared. That's multiplying the whole equation by a minus sign, and that's not the same thing. So again, here we simplify exactly the same way. We end up with the minus 1 coming out in pairs, and the y coming out, y is y squared. And minus 1 times minus 1 is positive 1. And so, again, this simplifies to exactly what we had before, and that is our x-axis symmetry. In the origin symmetry, if we start out with y equals x cubed, which was that first example that is origin only, we're going to replace y with minus y and x with minus x. Now, in this case, when we simplify the x cubed, again, keep in mind there are 3 negative signs. And that means we're taking out essentially 3 negative 1s. And 2 of these cancel in pairs, but that leaves us with negative x cubed. But that means negative y is equal to negative x cubed. And if we multiply both sides of the equation by -1, we end up with y equals x cubed. So we're back to the equation that we started with, but because we had a minus sign on one side of the equation and a minus sign survive on the other, they canceled each other. Now, the circle equation was this. And so to test for origin symmetry, we would replace x and y, again, inside the squares. And just like we saw before, you end up with two negatives and -1 squared is 1. And so you get them to cancel out and you get back to your original equation. And again, this one, there's no extra minus signs that we're canceling at the end. It's the x is canceling and the y is canceling separately, and then we're getting back to the same equation. So in both of these cases, we have origin symmetry. Now, this last one in particular, and the one that we looked at for the x-axis symmetry, these are examples where we actually have relations and not functions. And so when we actually only look at the world of functions, x-axis symmetry is not possible, because if we look at the graph of our functions that had x-axis symmetry, so that would include this one, we see that it violates the vertical line test. It's not a function. And so this would not be something that we could actually deal with. Same thing for the equation of a circle. This is origin symmetric, but it's a relation because it also violates the vertical line test. So when we are dealing in the world of functions only, there is no x-axis symmetry. Because any function that had any equation that had x-axis symmetry would not be a function. And so that reduces us to just y-axis symmetry and origin symmetry. And only origin symmetry that was independently origin symmetry and not because it's x and y combinations. Now, because there's only two of them, and it turns out that there's the relationship between, for instance, the degree of a polynomial and whether it's origin or y-axis symmetric, we refer to y-axis symmetric functions as even, because functions that have this property are things like x squared, x to the fourth, etc. And origin symmetry are referred to as odd functions. And the reason for that is because sort of a typical example of odd functions or odd symmetry is for polynomials that have odd powers. Now, these are not the only ones that have or x-axis symmetry or y-axis symmetry, or y-axis or origin symmetry, but these are sort of the quintessential examples of things that have the appropriate kind of symmetry. So y-axis and even symmetry are exactly the same thing. If I talk about an even function, I'm talking about a function that has y-axis symmetry. If I'm talking about an odd function, I'm talking about a function that has origin symmetry, whether or not it happens to be a polynomial or not. So examples of even functions. So these would include things like constants actually, because they're polynomial of degree 0. Um, X squared functions with or without a constant. Not with a linear X term, but with a constant would be fine. Absolute values. As long as you're not shifting the absolute value away from the origin, if you're moving it up or down, you're good. If you're moving it side to side, that's going to break the symmetry. But those are all examples of even functions. Later on in trigonometry, we will see that cosine of x is also an even function. And examples of odd functions would be things like, again, linear functions. If you are moving it anywhere, basically, you're going to break the symmetry because constants are even, so they're going to destroy the odd symmetry. You could have cubics with linear terms or without linear terms, that would be fine. You can have reciprocal functions. Those are odd symmetry. Also, when we get to trig functions, we'll see that sine is an odd function. And again, we could plot each one of these and we would be able to see that, of course, they satisfy the equation, they satisfy that symmetry graphically. But if we want to test them algebraically, the test for even functions is expressed as f of x is equal to f of negative x. So again, this is just that idea of we're going to replace x in the function with negative x. And when we simplify, we get the same function back. And the test for odd functions is negative f of x is equal to f of negative x. And again, this is basically saying if I plug in negative x on the one side of the equation, I get a negative sign that survives. And so by replacing y with negative y, that y is going to cancel, that negative is going to cancel with the other negative. So let's just walk through. We'll do the x squared minus 1 example. So if I replace negative x in my equation, and I'll just do g since we're going to do that example, negative x squared minus 1. Again, negative times a negative is going to give me a positive. And so I get the same equation back. So again, this confirms that it is even. And if I do this for my other g function, g of negative x, then I'm going to get negative x cubed minus negative x. And that's going to get me a negative x cubed because two of my negatives will cancel, but the third one will survive, plus x. And that is the same thing as the negative times my original function. And so if this was my original function, and if I plug in a negative on this side, I get the negative of the original. This is an odd function. This has origin symmetry.